Hi, welcome to my design project for 2PO4. So the question here asks to find the twist angle and moment for this hollow cylinder here. We're given the dimensions here, the material properties, and the applied distributed stresses. So for part A, what we need to do is we need to find the moment at the top face here. So we start by finding our differential force, and we cross it with the with our position vector, and then our result is that we have a differential torque here, and we can see that there's no x and y components of the differential torque, which means that our stress is going to be purely torsional, and we have a illustration that shows how the stresses are applied here, and they're moving in the clockwise direction, also known as the negative direction, since that's how we defined it. And so to find the moment, what we need to do is we need to integrate the differential torque over the top face here, over this area. So what we did is we just we integrated it over the using the large radius and just treating it as like a full circle, and then just subtracting the moment of the inner radius, and that's what we did here. And so the total moment we got was minus 391,000 Newton meters. Um, and it's fairly large, which is expected because they're acting in the same direction, and it's negative because it's the forces are applied in the clockwise direction. And then so for part B, we need to find the twist angle for the beam on the top face, and to do that we can just use Hooke's law of torsion, and then we just rearrange for the twist angle, and then we know that the torsion constant is equal to the torsion constant for a ring cross section is equal to this. We know that from our notes, and then we know that the Young's modulus is related to the shear modulus with this equation, and then we just let Maple solve for the twist angle. So we get a fairly small twist angle, and it makes sense because the Young's modulus is relatively high when you compare it to the forces that are applied. So basically, we have a very strong structure, and we don't have that much force that's being applied on it. So it wouldn't twist that much, or sorry, that much stress being applied on it. And it makes sense that it's twisting in the negative direction because the forces are once again applied clockwise. So, and for part C, what we need to do is we need to find the twist angle in flex. Um, so this creates our cylinder. It was given in the question. Um, we just put in we just define our variables here, define the loads, and then we use this to find phi, and then we define x prime as the original x plus its displacement, and similarly for y prime, and then we just rearrange this twist angle formula to get theta, and then we just let Flex solve for it, and we did a magnification of 20,000, and the results we got are shown here. So Flex is showing us that there's some warping going on, but it's magnified 20,000 times, so it's almost negligible. And we can see here that it also shows that the twist angle is non-uniform. Um, but when we look at it more closely, we see that this purple part and this and the red part here, they vary by like a very, very small amount. So we can just kind of ignore that, and we could just take the middle part, so basically the green part here, as the average twist angle. So we got a result that's almost the same as our maple. It's a little bit larger, but it it's probably likely due to the fact that in flex, when you apply stress to a face, it won't rotate with the face. So the angle that it's applied at changes a little bit. So that's why we have a little bit of variance. And so here we just compare our results. We see that in the flex result was like a 4.7% bigger than our maple one. And reflecting on our topic, um, I think this was a fairly important topic to touch upon because as an engineer, if you're designing a machine, and it has some parts that are rotating, you want to know how much torsional stress those parts can take so they don't break, and so that you can choose the correct materials for that part. Yeah, that's it.